Alright, what we got in today's video is a recap of the algorithm for integrating a product. It's a reverse product rule. It's classically known as integration by parts because what we're going to do is we're going to take two different functions that form a product of each other, break it up into two different parts, and integrate. Now the origins and where this particular algorithm comes from we talked about in class, but again for this video we're going to explore just how to apply the algorithm in the best possible way. So in the first instance, again, here's the algorithm. We have two different functions, a u and a v prime. So when we're given the x and the square root of x minus 2, we have to choose one of them to be u, so that could be the x or the square root of x minus 2, and then whatever one we don't choose, that will be the v prime. So here are our options. We could choose either or, and in each case we have to find either level up or level down. So in other words, if I choose u to be x, then a derivative of u is 1. If I choose v prime, then it must be the square root of x minus 2, which we would have to find the antiderivative and call that v. The other choice is I could take u, take its derivative, take x, take its integral or antiderivative, and we get 1/2 x squared. So which should we choose? If we set up the algorithm, again the first two are u times v, so I look at my square and I find u times v, which is x times 2/3 x minus 2 to the 3/2 power. So I choose that, and then I subtract the integral, because that says subtract the integral of u prime v. So I take the u prime and the v. I get that. Now the alternative is to integrate the u times the v, a minus, and so forth. And what I can see here, between the two choices, the first choice is better, second choice not better. Why? Well, in the second choice you see here, I now have an integral with x squared. I've made a higher power, a bigger product, I made things more complex. Whereas here, I just have the integral of a simple rational function, or sorry, a power function. So, I'm going to continue on, I'm going to abandon this course and continue here. Now, over time, you'll be able to, and some of you probably right away, over time, you'll be able to choose your u and your v prime values by looking ahead, by thinking forward. But I'll show you some instances where perhaps intuition might be countered by the way things work in reality. But anyway, so here I have, again, this algorithm. All I have to do now is clean up this. So I have the 2/3 x, or the 2/3 x, and x minus 2 to the 3/2, and then I'm going to take the antiderivative of all this stuff, give it here, and add the constant. Clean it up for cosmetic purposes. Here we'll observe that I was able to take out common factor, whatever is the lowest power of the x minus 2 to some power, I divide out or factor out that to the lowest power. So here's the x minus 2 to the 3/2 power. That leaves me with 2x plus over 3 here, and then 4/15 here, and then there's an extra x minus 2 factor here. It looks a lot nicer when you see it all set up like that. So that leaves us with this. And I'm a little suspicious, it all looks kind of funny. I mean, it doesn't really look like, this would be the integral of that, so I go on to Desmos, and I put in the derivative of f of x, where here's the function f of x. F of x is my answer. So take the derivative of my answer and see that it gets me back where I started from. And I see only two graphs here because the purple and the green are in fact the same. Or sorry, the blue and the purple. Anyway, now I'll just focus on the algorithm itself. Here again, really straightforward. I'm going to choose my u and v values, u and v prime values, according to the fact that to take the derivative of x, it gets to a lower power, making things less complex. Before I proceed, I'm going to lay it all out and make sure it gives me something I want. And here we end up with the integral of a trig function, nice and easy. So I clean it up a little bit. Well, not yet. I'm just going to take the antiderivative. Notice here again the chain rule. I have 1/6, but I also have to divide by 2 to undo the chain rule for the antiderivative process. And cleaning that all up gives me this integral. All of this, of course, can be supported with technology, but I want to continue on with the video. Here is where we start to get into some creative uses of this algorithm. You saw it before that we were looking at instances where we had the product of two functions. Here's a linear function and a trig function. Here, we don't have the product of two functions, it's just the natural log of x. The way the algorithm is applied is to insert the 1 times the natural log of x and make v prime equal to 1. Now that seems counterintuitive because what I have to do next is integrate that, or anti-differentiate that, so I've increased the power. Until I see again now that the natural log's derivative is 1 over x, so the increase of the power to making this x is going to be counteracted by the 1 over x. I'll show you. We have the u times the v minus the integral of u prime v, and the x and 1 over x divide out, and we just have to integrate 1. And there's your integral. So the original use for the integration by parts algorithm was to work with products, to integrate products, but it can be applied to a product by 1. Here, I see something that I almost thought was the cosine of x times the natural log of x, and I was about to use u and v and all that until I recognized that this is the cosine of the natural log of x. So another question. Now, you have a couple of choices here. You could walk away right now and never think of it again. You can pause the video and give yourself an opportunity to attempt and see if you can find the solution, the integral of this particular odd-looking function. Option 3, of course, is to sit back and watch it all unfold before your eyes. So, what have you chosen? Well, if you're listening right now, you chose the lazy route. Watch it unfold. Unless you're listening right now and you tried it and you gave up. Or you tried it and you magically came across the solution. I'm sorry, I'm just messing around right now. Here's what I did. I was just exploring, and I took the derivative of the thing I'm supposed to integrate. I just wanted to see what happens. So I'm going to apply the algorithm. Maybe I can try that trick that I used with the natural log earlier. And I don't think there's anything else I could possibly choose to do, so that's what I'm going to do. I'm going to let v prime be 1 and then integrate upwards. This creates something that does not look all that good. I mean, on the one hand, I did get the 1 over x times the x to divide out to 1. So that's all good. But now I'm stuck trying to integrate sine of the natural log of x when I was starting out with cosine of the natural log of x. It doesn't seem like I've made it any better. There's still a way out. There's still a solution. You can pause again. Here's another chance. Can you figure out a way to get to this integral solution? Alright, I'm going to keep going. What I see here, I'm thinking ahead, and I see something, and I'll show you because I'll let it unfold. I'm going to do the same exact thing to integrate the sine of the natural log of x that I did over here. So, the u, the v prime, the v. The u prime over here. Anyway, that gives me this whole chunk here. I'm going to pause the video for just a second so that we can see this entire chunk right here is now integrated by parts. So here's the entire algorithm that substitutes in for this piece. We still carry over from before the work that we were doing in the earlier integration by parts. So now we have all of this, which cleans up nicely. And there again, an opportunity. I see that we've sort of spiraled into a loop here because this is the thing that I'm trying to integrate. So, here's what happens. I look over here and I see the exact same expression over here, the integral of cosine of the natural log of x dx